Hi everyone. So we're ChemSoc are just going to be hosting this HeadStart to research, and we're going to have a few lecturers just talk about their research within different sectors. So at the end of each talk, we're going to just do a 5-minute Q&A. So you can ask any questions you want then. And then later on at the end of the afternoon session, ChemSoc will just like hang around. So if any of you haven't started university yet, you can ask some questions then if you'd like to. Yeah, and can we just, Fabs, if you could click to the next slide, please. Yeah, so this is just the schedule for today for everyone to see. So it's definitely a bit of a drop-in sort of thing. So feel free to come to whichever of the talks you think might be most beneficial to you or most interesting. But I think they should all be quite good. So if you have any questions throughout each talk, feel free to type them in the chat. Or if you want to, at the end, we can ask you to unmute, or we can unmute you and you can like say them if you want to. You can have your cameras on if you'd like to, but if things slow down technology wise, we might ask you to turn them off. And Fabs, if you could click to the next slide, please. Yeah, so this is just kind of summary. Yeah, that's everything from us. We will pass over to Professor Abbott now to say a few words.
Fantastic. Well, thanks a lot for inviting me to say a few words today. So thanks to the ChemSoc and also to Fabs for putting this event together. And I think there are sort of two things that we want to try and highlight from undergraduate research. So the first is that it's very important to the department in terms of its outputs, and also it's very important to the students in terms of their overall employability in the subject. So in case you sort of haven't had any experiences so far, and you don't know what undergraduate research is about. So typically for the BSc projects, and there's an 11-week project, and for the MChems it's roughly a 20-week project. And also there are other experiences where students very often will do a summer piece of work. We're also introducing a course, hopefully the year after next, when students can get credit for doing work as part of their undergraduate course during the summer or Easter. And of course, students also get some experience of research when they go and do a year abroad or in industry. Just to give you some idea as to the sort of impact that you can get from that. So I was sort of tossing up through my CV the other day, just how many papers I'd published with undergraduate students. And although I've got about 200 papers, 30 of them are published with undergraduate students. I'm literally at this moment just finishing the 31st with a student that has been employed in a Faraday Institution project over the summer. And she's written authoritative research review on debondable adhesives. And so also, if I look to the department's outputs in terms of impact, so I'm a little bit embarrassed to sort of say that the most cited paper from the department is work that came out of my group. And in fact, the work which appeared in JACS at the end was carried out by an undergraduate student, David Boothby, and it's got well over now 2,500 citations to it. So if any student was thinking, what impact can I have? You can have a very large impact even during your undergraduate times. In terms of the project itself, the most important thing about doing research is that it develops all of your employability skills. So the biggest one, of course, is problem solving. And clearly it's writing up of projects, it's presenting your work it's working within a team, and it's your organization of your daily skills, your sort of time organization, and all of these are really vital skills that you will want to try to get across in your CV later. What many students worry about when carrying out research is that it will label them. You know, I've got a project and I don't want this project because it will label me as an organic chemist or a physical chemist. Try not to label yourself. So I'm in theory, card-carrying physical chemist, and as an undergraduate, I have written in my undergraduate notes somewhere, I hate electrochemistry, I never want to do it again. And many of you might also have those notes written in your notes. But believe me, you know, you'll meet somebody who will hook you into the subject. And I met a very mad Argentinian who just made me into an electrochemist. So try not to have sort of preconceived ideas and just do research for the fun of it. So I don't even have a GCSE in biology, but I've published sort of in medical journals and in pharmaceutical journals in the past. So be active as part of your project and enjoy it, and have an open mind. Don't sort of say, oh, I hate physical chemistry because Professor Abbott taught it to me. Have an open mind and just sort of see what some of these projects are about. So I hope you enjoy today, and I hope it's the start of a very long and active research career for you. So thanks again to everyone for organising it.
Cool, thank you very much for that. So we have a few minutes before we can properly start, but if anyone has any questions at all about how the day is going to run or anything like that, now's the opportunity to ask. Feel free to pop it in the chat.
I guess I could just say a few words, if that's okay, Rosie. Yeah. Just following on from Professor Abbott about employability. As many of you will know, I'm the careers tutor and the placement tutor as well. So this thing about labeling is also quite interesting, because a lot of the projects that we have within ester chemistry are very multidiscipline, interdiscipline research. So you may traditionally think of organic, inorganic, physical, but clearly you've got physical chemists that are working in medicine, and you've got other chemists working in the environment, in food, even in security and defense. So this kind of thing about labeling is actually quite interesting. So when I do start my presentation, it's going to be very much focused on sort of application. But it can't just be done with chemists alone. You need engineers, you need computational chemists, you need mathematicians. And I think when you do some of these research projects, you get an insight in the variety of different areas. And you're not in a position really to think about, well, I'm this chemist or I'm that chemist. Usually you have quite a broad brush with quite I'd say a diverse array of skills, transferable skills that you've learned that hopefully will lead to sort of meaningful and really interesting careers after you leave Leicester.
I think to build on Karl's point, so we run many very large projects. So Karl and I are part of a £100 million government-funded project looking at the future of electrification in batteries. And as part of our project, we're working with not only scientists, but also sort of social scientists. So we're looking at sort of recycling of car batteries, but you also work with lawyers, for example, in terms of as soon as you produce a used car battery, it's then a hazardous material. So you then have to look at sort of the law associated with moving materials across borders. You work with economists. You work with social scientists. A lot of my group are now working on looking at techno-economic analysis, so how much does it cost, and also life cycle analysis. So it's looking at the whole process in terms of how much energy goes into a battery, and is it actually green? So yes, so as Karl said, that it's a huge amount in terms of cross-disciplinary working. We're even working with biologists who are trying to work out, can we use enzymes to digest batteries. So definitely don't label yourself. Certainly don't even think of yourself as a chemist. Just think of yourself as a curious mind.
Okay. Yeah, that definitely makes a lot of sense. Okay, so if nobody has any questions at all, then we can get started. So first up, we have Dr. Karim, who's going to be talking about his research in spectroscopy and atmospheric chemistry. So, Karl, if you are ready, you can unmic and everything.
If you hang on a sec, I'll just share the screen. I don't think I'm able to share my screen, so hang on a sec. Right, if you just wait for a minute. Right, so can everybody see that?
Yeah.
And hear me clearly?
Yeah, very good.
Yeah.
Brilliant. Okay, so Professor Andy Abbott spoke about labels. So I work in Leicester Biotechnology Group, and I probably could have presented in any one of the different chemistry themes that we've got within the School of Chemistry. And that just really sort of indicates the kind of sort of diversity that we even have, even within a small group within the School of Chemistry. And you magnify that in chemistry as a whole, you can see that we're touching a lot of different application areas. So my presentation that I was asked to do was talk about the kind of work that we do in the Leicester Biotechnology Group. And my title is about how you design smart polymers that have memory. So normally when we think of polymers, we think of plastics, hard plastics, but I'm really talking about how you make them smart. And I'm going to focus predominantly on the applications of the research, which gives you an insight into what you might do in a project, but what you also might have as a career. So what I'm going to talk about to start off with is just give a little bit of a definition about what molecular imprinted polymers are, which is the focus of the talk here. So molecularly imprinted polymers, so we call that MIPS, as you can see here. And these are polymers or pieces of plastic, essentially. If you think of something like grains of salt, that's the kind of size of particles of polymers we're talking about. They have been designed specifically to recognize a molecule, and that molecule can be a variety of different things. And often they're called plastic antibodies. They have an imprint that can actually memorize the molecule, and the molecule of interest is often called the target or template. So I'll call it template. And I put this funny thing here, Jennifer Lawrence's hands. Well, here's Jennifer Lawrence. She's imprinted her hands, her right and her left hand. So this is the principle of molecular imprinting. And the template is Jennifer Lawrence's hands. The imprints are her handprints, her left and right. The matrix, which would be like your polymeric mixture, is actually the cement. You also have a racemic imprint because she has the same number of left hands as she has right hands. And we also think about something being specific. So the right hand will fit the right hand imprint, but not the left hand. And then selectivity. So Liam's hands, who's sitting beside her or standing beside her, are too large to fit her hands, so to fit her imprints. So that's essentially the principle of molecular imprinting. Why do we want to do molecular imprinting? Well, MIPS share characteristics of antibodies. So we have a lot of biologists, a lot of medics that work on antibodies. And what we really want to do is have the kind of selectivity of recognition and binding of an antibody, but use chemistry in order to develop something that is often called a plastic antibody. No animals are used in their production. The MIPS are generally very tough. They're tougher than antibodies because they can withstand extreme pH, temperature, and pressure, because essentially they're pieces of plastic. There's many potential applications, and I'll get onto them a little bit later. And it offers the most generic and versatile, scalable, so you want to scale them industrially, and cost-effective approach to the creation of synthetic receptors. So MIPS are often called synthetic receptors. And what do we mean by that? Well, when you look at biology, you have a natural receptor. So you actually have a receptor where maybe a drug combined. So this green bit is a cavity where a drug or a molecule combined. Okay, so that's, you normally design a ligand for a receptor that is known, whereas what we're doing in the School of Chemistry, actually we're designing a receptor for a ligand that is known. Okay, and I lead the computational design, so I actually develop the recipes that are needed in order to synthesize these polymers in the laboratory before the chemist goes into the lab. So a little bit about the chemistry. So essentially you have functional monomers that have double bonds, they're polymerizable. So we're using polymer chemistry, radical polymerization chemistry. And you have your target, which is what we call the template, and a complex forms, non-covalent interactions of the monomers with the template, and you induce polymerization. And once you've induced polymerization, you can then remove the template that is bound non-covalently, so you just need to use very mild acid or base or a solvent that can actually remove the template, and then you're left with an imprint that is complementary to the shape of the target. That is called molecular recognition, and that is a molecularly imprinted polymer. If you wanted to go in the lab and make them and synthesize them, this is a rudimentary rough and ready method where not necessarily a specialist scientist needs to come into the lab and do that, but essentially you have your solvent, you add an initiator for polymerization, you add your template, you add your monomeric mixture, you put it in the test tube, you bubble nitrogen gas to purge any oxygen that can scavenge the reaction. You then seal it in a tube or a glass bottle, and you heat it up, you induce polymerization, you end up with a solid lump, which you can then get a hammer and you can smash if you want, and then you can sieve and grind and come up with a particle size of anything between 10 and 150 microns. So a little bit lighter grains of salt, that kind of size. If you can keep that in your mind, that's really important. And then you can do a little bit of washing, you can remove the template that is in the polymerization mixture, and then you've got particles that have those imprints on the surface. Okay, so that's a rough and ready method. What do they actually look like? Well, they can look like a variety of things. They can be materials that look very grainy that you can put in a cartridge. They can be something that looks like a membrane. So for example, any of you that are wearing contact lenses, that's still a polymer, but it's a very flexible polymer. You can also have the MIPS on the surface of sensors. So this is an etching where the surface has been etched or the polymer has been removed, so you can actually see that there's a coating. They can look like honeycombs, they can look like beads, or you can integrate them onto plastics. This is a microplate that biologists that use in order to do experiments on a microplate. So you can see the green is where we've introduced the polymer on the surface. So what have we done? Well, we've looked at lots of different things. So we've looked at sort of pharmaceuticals and drugs of abuse. Those things are really important and interesting. We've looked at metabolites that are really important to show function of organs in the body. We've looked at a variety of toxins as well, man-made toxins or natural toxins. We've also looked at things like proteins, as I mentioned here, and even things like explosives for security and defense. So these are the targets that we've looked at. And where does MIPS fit in generally to the area? Well, if you think about if you wanted to make a device, for example, then you need to have materials that can have some kind of recognition once you introduce it onto a sensor. So people use tissue cells, they use a variety of different nanomaterials, and MIPS has just become another tool in which you can use in order to develop an instrument or something that recognizes that molecule. So I've noticed that they're the top of the screen, which I can't remove, which is unfortunate, but these are examples of MIPS that we have worked on that have some form of commercial application or actually give you an idea of the diversity of the work that we do. So using these examples, we've taken MIPS and packed them into cartridges, and we've been able to detect a variety of different toxins that you find either in food or a variety of different other things. So many of you may have eaten some of these toxins already this morning, if you've eaten any of these, and they're in very low limits, which is fine. They don't really affect you. But once they're above a particular limit that is regulated and controlled by the EU, then you can start falling ill. So what we've done is we've packed some MIPS in cartridges that we've made specifically for these types of toxins. And then you can put them inside a machine and you can actually detect the presence of these toxins that are fluorescent at parts per billion level. So that's a very interesting way of using MIPS for food sensing and food diagnostics. Can everyone still hear me?
Yes.
Yep, that's good. That's fine. I'm finding it difficult to remove the top bar there, so hopefully that is not there. I don't know whether you can see my titles of my slides.
Yeah, we can see the titles.
That's brilliant. Okay, so I said about cartridges. So what actually happens inside a MIP when you pack it in a cartridge? Well, if you have a look here, you've got a sample that usually has your target of interest, which is your analyte, which is your template, which is in red, but usually it's a cocktail, and there's so many interfering compounds that are there. And what you can use is you can use the cartridge that has been designed in order to trap the analyte, which is in red. And when you pass the sample through, then obviously the imprints bind the red triangle, which is your analyte, and all the interfering compounds come through. And therefore, you can either measure the presence of the analyte actually on the cartridge, in the cartridge, or you can add another solution and you can selectively elute the analyte, which is now pure. Originally, it wasn't because it was contaminated and it was in a cocktail. Then you can use a variety of spectroscopic techniques to look at the presence of that molecule. So that's a really simple way of explaining it. The third example I just wanted to show you was really about food and how you can turn waste and make it into a high value commodity. So one of my colleagues, Dr. Elena Paletska, she actually was able to isolate curcumine, which is actually found in waste potato peels that industry throw away. Curcumine is able to reduce your blood pressure and is also has antimalarial activities. And we were able to extract the drug from potato peels with about 90% purity. So we're now taking waste from food and actually turning it into a valuable commodity, which is a drug that can be used. The other example, we're talking about now imprinting larger molecules. So we can imprint viruses, and viruses are really large molecules. So you can pack a sample of water, for example, that's got a virus in, and you can pack cartridges that can bind the virus. And you can see here that there's 4 × 10⁹ virus particles in the sample, but when you pass it through the MIP, you've got hardly any virus at all. So the cartridge has bound the virus and now the water is clean. So there's lots of things like that you can do with bacteria and viruses. This is one that was very interesting that we also worked on, was actually taking these pieces of plastic and using them as antibacterials. So very quickly, quorum sensing is a way in which bacteria communicate and coordinate behavior. They secrete small signaling molecules, that's their language. And they're called homoserine lactones here. And about 65% of all human infections emanate from a biofilm forming. Lung infections, pneumonia, UTIs, persistent wounds, and tooth decay. So this is a very simple cartoon of the signaling molecule, and you've got bacteria. And what happens is they communicate with each other. So we essentially made a polymer. You could think of it as a sponge that actually has imprints for that signaling molecule, and the polymer binds to the signaling molecule, and the bacteria don't communicate, and therefore they don't build up a colony, they don't become virulent, and then they don't attack the host organism. So it's a very simple way of creating a polymeric sponge, in essence, where you can bind the signaling molecule. Now, one of the students, actually one of our undergraduate students, asked, well, what happens when the polymer becomes saturated and packed with the signaling molecule? Then the bacteria will grow, won't it? Because now it's completely saturated. There are no more imprinting sites to bind, which made us think about what to do. So what we did was we actually imprinted the transition state of homoserine lactone, which is the signaling molecule. And what we were able to do, we were able to hydrolyze the signaling molecule that gives you a molecule that has no biological activity. Now, that signaling molecule will degrade in nature naturally anyway over a number of hours, but our MIPS have actually accelerated the hydrolysis of that. So if you're hydrolyzing their signaling molecule, then you're going to reduce the bacteria from interacting with each other. We worked on a bioluminescent bacteria, and if that bioluminescence drops, then you know that the signaling molecule has disappeared, and therefore communication has been disrupted. What can you do with that? Well, you can take our polymeric particles, you can put it on paint, you can put it on door handles, you can put it on taps, for example, in hospitals, and that can affect the way in which the bacteria get spread in a clinical environment. One of the things I now wanted to move over towards is nanotechnology. So everything I've spoken about is sort of micron particle size, and I'm going to explain briefly about why we're now moving towards nano. So if you think of sort of the size of things, this is sort of a nice slide about the size of things. So what I've already described are micron particles, but if you start going to smaller things like talcum powder, blood cell, a virus, wavelength of visible light, size of a transistor, other viruses, you can then see that what I really want to do is try and make MIP nanoparticles that are significantly smaller than the ones I've already described. And how do I go about doing that? Because the chemistry now changes completely. So we're not using sort of the traditional chemistry that you might think of. So we have to start thinking about how do we control synthesis and how do we actually prepare nanoparticles that we can use. So what do we want to do, or what can we do? Well, we want to control the polymerization chemistry. Normally when you polymerize something, it's an uncontrollable radical polymerization reaction, and you end up with a solid lump at the bottom. And essentially that's what I've shown you. You end up with a solid lump, you actually wash it and grind it, and you end up with particle sizes. So you start off with a monomer, you end up with a very hard polymer at the end. And what we really want to do is find a way of producing nanoparticles where we can automate their synthesis so we don't get batch to batch variation. We want to develop nanoparticles that are multifunctional so we can use them in a variety of different things. But if they're water soluble, then what happens is it allows us to use our MIPS or nanomips in biology and in medicine. So that will be in sensing and it will be in diagnostics. So what we want to do is stop the polymerization around here. So you end up with very small molecular weight nanomaterials, maybe even oligomeric. But at that point, they're water soluble, but they still have molecular recognition. And at this point, it's too late. You can use them as cartridges, you can use them in HPLC, for example. But in order to use them in biology, this is exceptionally limited, practically impossible. But here it opens up the area of biology that we're working on. So how do we do that? Well, a very simple way is we use something called solid phase synthesis. So those of you that know a little bit about protein chemistry or about making peptides, we use solid phase synthesis in order to make our nanomips. So these are just glass beads, which are very cheap and are quite cost effective. And you covalently attach the target of your interest, which is your template. You add a variety of reagents, and then you shine UV light, so it passes through the glass, which induces polymerization. And then you have low affinity nanoparticles that are not really very useful, and you wash them away in acetonitrile here at quite a low temperature. And as you raise the temperature of the column and the solvent, you could then wash out and collect the high affinity nanoparticles. It's a very simple way of doing it. And we've developed and made an automated machine that can actually synthesize batches of nanoparticles with very little deterioration in performance and also the size and shape. This is an SEM showing you that the size and the shape are quite uniform. So the cycle is about 3.5 hours. You put your reagents in and you end up with a pot of nanoparticles at the end. The beauty is that the template that is immobilized on the surface of the glass bead can be reused. So if it's a virus or a protein or a peptide that is very expensive, you can regenerate the column and then make significantly more nanomaterials. And you can make research quantities and they can also be scaled up. And this is what some of our BSc project students and our MChem project students and obviously our PhD students have been working on. So why? Well, if you think of antibodies, their lifetime is not great. Storage in a freezer, you can't really regenerate them. Sterilization is problematic and the price can be very expensive. Whereas we've made MIPS that haven't deteriorated in performance over years. You can leave them in ambient temperature, you can regenerate them, and you can use very stringent conditions in order to autoclave them or sterilize them, and the price is several orders of magnitude cheaper than an antibody. So we want the characteristics of an antibody, but all of those other advantages. And those advantages are fantastic. So this is the future, and this is what I'm going to finish the presentation on, which is about how we use our nanoparticles in medicine. So this is a human cell. We've got MIPs that have been fluorescently labeled that are red. And if you go through the diagram here, you've got the nucleus of the cell, you've got the cytoplasm on the outside, you've got the rhodamine, which is a fluorescent molecule, so the MIPs are red, and at the end you can see that there are red patches within the cell, so therefore we're able to get MIPs into a human cell, and that then opens the area of us to use them in biology. So they're water soluble, they have uniform binding size, they're small enough to enter a cell, and therefore you can now start using them in medicine. So one of the examples that I wanted to give to you was actually breast cancer cells that have an overexpressed EGFR. There are antibodies that work efficiently against breast cancer, but they tend to be unstable, and there's very high production costs, and therefore those are the drawbacks in clinical use. So we made nanoparticles that can detect and bind using a fluorescent molecule. So the nanoparticle is fluorescent. We've made an imprinting site for the drug, doxorubicin. So the MIP actually has the drug bound and within the imprinting sites. But we've done a second imprint where we've also imprinted the EGFR, which is a very small fragment called an epitope. So the MIP in this diagram actually can bind to the recognition site and then has the drug doxorubicin that it can then release. So it needs to get to the right place, and then it needs to deliver its load, which is the drug. So they elicit cytotoxicity and apoptosis only in those breast cancer cells that have this overexpressed EGFR. So that's the kind of thing that we can do once we can make them compatible with water. And there's a paper there that you can have a look at to see what we've done in more detail. So the potential applications, well, research tools for analysis of molecular interactions, diagnostics, which is sensors and assays, imaging, drug delivery, pharmaceutical, purification, and catalysis. So the area is a broad platform technology, which means that it is really dependent on the type of target that you're looking at. So if you're looking at food or environment or security, defense, and medicine, it's dependent on the target. So we can adapt for the different application areas. But these are the kind of areas that we see people who work in our area, work in industry in those particular application areas. Acknowledgements, Professor Sergei Peletsky is the head of Leicester Biotechnology and Dr. Elena Peletska, so they've contributed significantly to these slides. Numerous sponsors. We also have a spin-out company called MIC Diagnostics based on the technology, and I know they've just recently developed a COVID-19 sensor. If you want to read a little bit more about chemical biology or the School of Chemistry, then you can just have a look on the website. So I'm finished, so thank you very much for your attention.
Thank you very much. So we'll move into some questions. I haven't seen any in the chat yet, but I have one. So if MIPs have like quite a long lifetime, how is it not quite difficult to like try and get them out of the human body if anything goes wrong or if they're like no longer needed?
If you make them small enough, they can be excreted from the body. So we've looked at toxicological properties of them, and there hasn't been any inherent toxicological properties of these materials. If you make them small enough, then you can actually pass them through the body, go to the liver, kidney, and then you can urinate them out. There are a variety of other nanoparticles that you can use, making things like lactic acid, polylactic acid materials. But I think what you really want to do is have a nanoparticle that is robust enough for the molecular recognition to be in place. So if you make them too small, then the molecular recognition can be affected because the binding site doesn't sort of fit, it's quite flexible. But you need to make them small enough for biology. But in terms of sort of toxicity and the ADME properties, which is what we call when we're looking at these materials, we haven't noticed any adverse toxicity at all, even though we haven't done sort of any human trials or samples, but clearly we can get them into a cell and we can get them out of a cell and then we can get them out of the body.
Okay, so for the breast cancer drug that you mentioned, is that currently being used in medicine at the moment?
No, so a lot of this is at research stage, which is proof of concept, but it will be, and it can be. I think you first of all need to look at what the gold standard is. So if you've got a system that already works, that is quite effective, that is not particularly expensive, is commercially viable, then why would you ever make a MIP? Sometimes we make MIPs in areas where there is no diagnostic tool, there's no sensing element. But clearly, if you're looking at antibodies that are not always cost effective to use in therapy, and a MIP nanoparticle, 10, 20, 30 milligrams, 100 milligrams only costs a few pence to make, but has the recognition, and you can adapt the chemistry very easily to make new batches, then there's a potential then to commercialize it. With breast cancer or other types of cancer, you need to get the nanoparticle or any molecule in the right place, and then you need to deliver the drug. And with the nanoparticle imprinting and being able to modify and control the chemistry, we can actually control where it goes and also how it delivers the drug. So MIPS is just a sort of a new tool in nanotechnology or nanomedicine that has been established over a number of years. So we're following the kind of procedures that people would use in order to make a nanoparticle for either in vitro or in vivo.
So when you say it's like a relatively new tool, how new? Like
Well, it's not new. I mean, imprinting's been around since about 1938. So people have imprinted lots of molecules. So things like solid phase extraction, putting them on sensors, all of those things have been done. I think over about the last 10 years, there's been massive acceleration in actually making nanoparticles and nanomaterials. So what you need to do is find a way of being able to automate them so that there is not batch-to-batch variation, especially if you want to use them in a clinical or medical environment and you want to commercialize them. So that's the reason why we developed a machine. So if you've got the recognition, you've got the way in which you can report it, you can adapt them, so you can radio label them, you can make them magnetically labeled, you can optically label them as well, you can put fluorescent markers. That is really the sort of the gold standard that you need to achieve. And I think that's really been accelerated over the last couple of years. MIP Diagnostics have developed a COVID-19 sensor, so they're looking at sort of commercializing our technology. So if you look up MIP Diagnostics and see what they're doing, you can see the sort of the medical direction that us polymer chemists are moving towards. So when Professor Andy Abbott spoke about sort of the diversity, you wouldn't normally think that maybe a physical chemist or polymer chemist are actually working with clinicians and doctors across the road from our school, but they are.
Okay. Also, in terms of the fact that you've kind of gone to like the nano scale now, would there not be kind of more implications, like more negative effects in the body, because obviously like they're smaller so they can get around to other places, or is it relatively easy to kind of target them to where you want them to go?
If you think of modern nanomedicine now, if you think of nanomolecule and nanomedicine now, so you have usually, I think drug delivery is really the main focal point. So you can have a drug that is actually bound to your nanomaterial, but it needs to be released. So that linker needs to be hydrolyzed. You need to make sure that it has the recognition so it goes to the right place, and then you need to detect it. So all of those are the three principles of making a nanomedicine, on making a nanomaterial that's been established for over 10 years. So essentially all of our nanomaterials that we make have those three features. Okay,
that's cool. Does anybody have any other questions or comments they might like to say?
Yeah, I have a quick question for Karl. I mean, I really like the templating strategy in general, like just the fact that you can effectively decide what a target is and then just model your chemistry around the target and make it very flexible. So I guess the recognition part of the cell is pretty much sorted. So could you envisage even trapping a metal complex, let's say cisplatin, for example, inside another particle so that it's delivered to the correct cell and then it gets through and then you can release your metal-based drug inside the cell intact, pretty much?
Yes, you can. We haven't used metal-based drugs, but as long as you can look at it in a couple of ways. You can have molecular recognition that holds that in place, and then it releases it because of a local change in pH or something in a cell. or you can not use molecular imprinting and actually just create like a polymeric scaffold, a little bit like what maybe dendrimers do, and a variety of other nanomaterials, or a polymeric micelle, where essentially you've just got the drug loaded into a polymeric matrix and then deliver it. That's okay, but you need to have the molecular recognition. So I guess what we're looking at is using the properties of those nanomaterials that are currently in existence right now in medicine, where you're essentially saturating your polymeric material. But the recognition part is the advantage, is getting it into the right place at the right time, and then having some local change where the drug then can be released. Usually that's a small change in pH where maybe the polymer expands slightly and then the drug's released. And you have to remember that the drug that is bound is not covalently attached, it's non-covalent. So you only need very small perturbations in pH or even temperature, and then you can release the drug.
I'll check the chat again. So does anyone have any final comments or questions they might like to ask before we move on to the next speaker?
Can I ask if these are meant to be used for multiple doses, or is it sort of a one-dose situation? As take, for instance, the breast cancer one, is it a molecule that can continue releasing drugs over a period of time, or is it sort of a one-go, then repeat it?
It's a good question, because I'm not sure you want to continuously deliver drugs, because some of those drugs are actually toxic themselves. So they're cytotoxic drugs. So you can work out the concentration that you need in order to release the drug, which you would normally do under laboratory conditions by taking quantities of the drug, binding it to the polymer, looking at the way in which it releases, and the time that it releases and the concentration that it releases, and then making a nanoparticle that can release the cytotoxic drug within a particular clinical window, which is what we're guided by the clinicians. The thing about, I think what you're really saying is sort of controlled release over long periods of time. So I know one of the things that I was particularly interested in, some researchers' eyes, can you integrate nanoparticles, for example, into a contact lens? And if you can integrate a nanoparticle into a contact lens, well, a contact lens is hydroxyethyl methacrylate that is polymerized, so it's polyhydroxyethyl methacrylate. So essentially a membrane. We actually have that monomer in our lab. But could you integrate a nanoparticle with a drug, and you put the contact lens on, and it slowly releases either an antibiotic or a steroid into your eyes over 2 or 3 days at very low concentrations, in order to treat an infection that would otherwise be quite serious, where you may have to inject something into somebody's eye, because it can be as catastrophic as that. So you can have controlled slow release for a variety of different things in terms of sensing that are really outside of the body. But sort of in vivo, you want to be able to release a known concentration of drug within a particular localized area, and then the job's done. Switches it off, remove it from the body.
Okay. Well, thank you very much, Karl, for speaking today. It's been very, very interesting. Next up, we have Professor Karl Ryder, who's just going to be talking about some materials research that he does.
Hi, Rosie. Can you hear me?
Yeah, hear you.
Cool. So before I start, I'm just going to share my screen. So hopefully that will work. Okay, can you see, can people see my screen?
Yep.
Okay, so this is the challenging bit then. If I go into presenter mode, does everyone still see that?
Yep, all good.
Excellent, excellent. I do love it when things work. Okay, right, so I'll start my presentation then by saying another welcome everyone. It's good to see a good few of you here today. And my name is Karl Ryder, so I'm a professor of physical chemistry. I'm also responsible for a center which we call the Materials Center, which is a part of the School of Chemistry. But it's also a hub of activity for a range of activities and research themes that kind of go across the College of Science and Engineering. So this is strengthening this idea that our research is not just kind of narrowly focused necessarily in some aspects of academic interest, but actually more widely focused in things that we can contribute towards the development of new technologies. You've just heard about really exciting developments in terms of making new drugs and new treatments. So our activities in the centre are really focused on materials, the chemistry of materials particularly, but we collaborate in doing that with academics and companies. So academics across the schools of geology and geography, physics, maths, and engineering particularly. So we're very much multidisciplinary, thinking about various aspects of chemistry and how that can help to solve and address the problems that we see and face as a society. So within the building, we have a small building which is next door to the main School of Chemistry. There are three of us associated with the School of Chemistry who have our research groups based in the Materials Centre. And our activities really are focused on understanding some aspects of chemistry that particularly are important in manufacturing, in energy storage and release, and more recently in recycling. I mean, if you think about the way that we've changed as a society now, we're constantly thinking about how we can reuse, recycle materials. And really that's quite new to our society, certainly within the last sort of 30 years. More and more manufacturers, governments, legislation are thinking about how we make stuff, thinking about not only what we're using and what we're going to use it for, but how we're going to recover that material later on and save waste. And that involves understanding a lot of the fundamental science and the chemistry of these materials. So that's kind of where we are. I'm going to talk about, okay, I can't change my slide. Here we go. I'm going to talk about a particular aspect of that. I could mention lots and lots of different projects, but I'll talk a little bit about one of our focus areas, which is to develop new solvents as a way of processing materials and developing new chemistries within those solvents. Now, some of you may have heard of solvents called ionic liquids. These are relatively recent development in sort of social terms, again, within the last sort of 30 years or so. And these are essentially low melting point salts. So if you think of sodium chloride, it melts at about 800 degrees. These are liquid salts that typically have melting points below 100 degrees Celsius. And they have all sorts of really interesting properties. You can do some neat chemistry in them. They have essentially no vapor pressure, so they don't evaporate. And they've got great electrical conductivity, so really good electrolytes. And many other interesting chemical properties. In fact, there was an article in Chemistry World a few years ago that said that ionic liquids were one of the key innovations that were likely to shape the 21st century. So it all sounds great, doesn't it? Let's do this, except that these ionic liquids are really hugely expensive. So if you're thinking about maybe processing or scaling up chemistry, then these really are economically unviable. So one of our activities in Leicester has been to look at alternatives, which we've developed, and this is my colleague Professor Abbott, who you saw earlier, has been largely responsible for this. These alternatives to ionic liquids, which essentially have very similar properties, but which can be made and formulated and varied at a much lower cost. And that's really a key point here. We can develop these novel chemistries, these novel liquids at a much lower cost than conventional alternatives. And if you go to some of the literature, you'll see that we've published quite widely on this recently, and it actually has become a really diverse theme within the academic literature. So new electrolytes, they're new liquids for finding alternatives to some kinds of process chemistry. So what kind of processes are we talking about? Well, they vary in scope hugely. So we can think about doing polymer modification, natural product extraction, that's getting things of interest from natural sources, industrial processes like electroplating, so metal coatings, for example, and that's one of my particular interest areas. And in particular, more recently, recycling of materials through being able to extract and recover critical raw materials, particularly metals. But also interestingly, in the collection and development and use of forensic evidence. So one of our colleagues here has a particular interest in the materials associated with forensics. So making new materials to develop fingerprints more reliably from objects that perhaps were more difficult in previous times. And that carries on a rather nice legacy of forensic science within the University of Leicester, particularly following from the Alec Jeffreys stories for DNA fingerprinting, which I'm guessing most of you may be familiar with. So a huge range of these applications. And what I'll do is just kind of take you through a few of them. I'm not going to go into detailed chemistry. I'm kind of giving you the overview of how our activities are focused both on the fundamental science, understanding the chemistry, but also with an eye on what it's going to be used for. And in particular, we talk to the end users, we talk a lot, and we work with industry in those projects. And that's of interest for those of you who will be doing projects and studying with us as undergraduates, because often those projects will involve the industrial partner and often lead to publications, which Professor Abbott was talking about earlier. So I'll take you through a few of these. I'm known for overrunning in my talk, so I'll do my best not to overrun. But I'll talk to you about a few of the rather exciting and recent projects that we've had using these new liquids and new techniques, and our collaborations with industry in order to develop these new materials. So one of them then is this thermoplastic wood. So this is a kind of generic term for things like MDF. So even if you don't know what MDF is, you're almost certainly using it because most furniture, laminated furniture, flat pack furniture, the sorts of things that you see in shop displays, IKEA, all of that is made of, not all actually, most of it is made of a material called MDF. And it's basically a bunch of very small wood fibers compressed together with some binding resins that keep it in place. Great stuff, except that it's made with chemicals, including formaldehyde, which during the course of their use can be emitted as a vapor. And formaldehyde is really a very unpleasant material. It's carcinogenic, and as a whole, we would like not to use it anymore. So one of the projects that this has been driven by Professor Abbott was to use other chemical systems, so understand what's going on, how the MDF works, how it binds together with the chemicals in the resins. If we understand those processes, then we can perhaps design something which works just as well, but doesn't use these chemicals. And that's what Professor Abbott was able to do here, using components from these new electrolytes. So the picture at the bottom there is of a nice little cupboard that's been made from one of these thermoplastic woods, which is not MDF, but it works almost as well as MDF without having to use these rather unpleasant formaldehyde chemicals. Okay, so again, that kind of underlines this idea that we need to understand chemistry and the physical aspects of these materials. We need to understand those in order to be able to develop alternatives. So a combination of fundamental science and practical application. And that's, I think that's an image of the same material after it's been worn for a while. Okay, well, another example, and I mentioned it earlier, is natural product extraction. So this is a huge industry, not only for finding, for example, drugs for different medicinal applications, which often come from natural product sources, things like fish, plants, and so on. But also for chemicals that we might want to use in other contexts. So, for example, cosmetics. Quite recently, we worked with a brand new company who took these liquids developed in Leicester and used them to extract fragrances and other therapeutics, sort of almost like homeopathic therapeutics from a range of different plant materials. And they generated this new range of materials and a new company to market them. They call them Eutectic. Here we go. eutectis. So this is the process of extracting these natural products from plants using these liquids, and these are now on the market. So these you can buy these. I think these are French. You can buy these materials now, which have natural products in them, natural fragrances and so on, that have been extracted using these types of eutectic solvents. So no harmful organic solvents, nothing going up into the atmosphere through evaporation. A much more natural and much more sustainable process. And the company behind this is called Naturex. So that's another example. I move now to examples which are closer to my own area of interest and expertise. So I mentioned electrochemical processes. Well, most of you, as Andy said earlier, people think about electrochemistry, they sort of, the hairs go up on the back of the neck and they think, oh my goodness, I don't want anything to do with that. But many of the ways that we manufacture things and treat things are actually electrochemical. So if you see, for example, a large stainless steel vessel that might be used for making food, mixing food, or for making drugs, the likelihood is that it will have been finished and polished using an electrochemical process. And this is a process where the roughness of a surface is gradually dissolved away by applying an electrical current. It's called electropolishing. Hugely prevalent in manufacturing, particularly in automotive and aerospace. So these processes are used a lot in surface finishing. And there's a couple of pictures there. This is a large vat of an electropolishing liquid being used to process, in this case, automotive parts. So what's the problem then? Why would we be interested? Well, the problem is that if you do this commercially, you have to use a range of really very unpleasant chemicals: phosphoric acid, sulfuric acid, sometimes even chromic acid and HF, all of which are seriously unpleasant and rather toxic and often carcinogenic. So one of our focus activities has been to try to develop chemistries, electrolytes and liquids that are alternatives to these rather unpleasant industrial processes, but which do the same job. So we're trying to develop sustainable, more environmentally friendly, nicer to work with alternatives to some of these industrial processes. And that, in fact, we did with this. It's a success story. So we managed to develop an electrolyte that works just as well as this sulfuric acid, phosphoric acid mix, made from essentially antifreeze, which is ethylene glycol, and a chemical called choline chloride with that, which is actually a food vitamin for animals. So mixing these two things together, we end up with a liquid which functions almost as well as these strong acids, but which you can spill and rinse away. You could put it on your skin and it could rinse away and it wouldn't do you any harm. So you see that as an illustration of one of the things that motivate us. But again, in order to design those liquids, you have to understand the chemistry of what's going on. So it's the fundamental science that we work on that underpins the applications that we then take to our industrial partners. And in this case, our industrial partners were commercial electropolishing companies, but also aerospace companies such as Rolls-Royce, who we work very closely with. I'm keeping my eye on the time, so I'll move on, and I'm happy, obviously, to answer any questions on any of these things as we approach the end. So I've mentioned another electrochemical process here. So this is not now a polishing process. This is now what's called an electroplating process. So if you look at lots of, well, many shiny objects that you might see, for example, in a car, or mass-produced on bicycles, or other types of metal technologies, they often have coatings which are there either to make them look nice or else to prevent corrosion, or to make them smooth and shiny so they don't attract bacterial aggregation. And for many applications, particularly aerospace, automotive, and lots of other things, chromium is a coating which is being used, which is both durable, it's nice and hard, but it looks nice, it's lovely and bright and shiny. And again, okay, you might say, well, what's the problem? You know, if you look at the landing gear of an aircraft, for example, or one of these JCB diggers with the big hydraulic rams, you see them bright and shiny, those will be chromium plated. And that's done on a massive industrial scale. So what's the problem? Well, again, the problem is that the electrolytes they use for these chromium plating processes are typically chromic acid. And chromic acid contains chromium-6 salts, which is one of the most carcinogenic materials known. And it's still done today because there are relatively few alternatives, things that will do the same thing, but that doesn't use. So one of our, again, another project here that we worked on for a few years has been to develop chromium plating technologies using source materials that don't include this terribly toxic chromium-6. And that's a real challenge because it really does involve understanding the individual mechanistics of the chemical and electrochemical reactions that result in the deposition and the precipitation of the metal coating. So it's really hardcore physical electrochemical science combined with this interaction with our industrial partners. And through those interactions, incidentally, our process is now being scaled up. So I show you this picture here on the bottom left. It's actually a print roller. So our partner company in this are making chromium plated rollers for high speed printers. And they're using our liquid technology to chromium plate these print rollers in quite large volumes. So again, that's another example of the underpinning physical and science, really, what we're interested in as academics, but being translated into a kind of an environment which is socially important. Okay, well, I'm kind of going on, but I'll give you one or two more examples before I summarize. I'm looking again at the time, so I'm still all right at the moment, I think. Another metal coating that's really interesting to us as a society is aluminium. Okay, aluminium is one of the most abundant metals that we have on the planet. And it's great for coating things that stops them from corroding. And that's interesting in itself, but we haven't really got a lot of time to go into the depths of that. But plating or coating things with aluminium is a really great way of protecting them from the environment. The problem with aluminium is that it's really difficult to make in its metallic form. Aluminium is present as an oxide in the Earth's crust, but it's really hard to get it from its oxide to its metallic form. So that's really energy intensive, and something like about 18% of global energy consumption goes on making aluminium metal. That's why it's so important to recycle aluminium. Well, okay, so if we decide that we want to electroplate something with aluminium to coat it, we have to find a source of aluminium to do that. And commercially now, there are ways of doing it, but typically they involve organic solvents, which are often volatile and flammable. And typically the source of aluminium that they use is very reactive, so that if you expose it to just air, it will spontaneously burn. So imagine the combination of an aluminium source, which is spontaneously flammable in air, with a volatile, flammable organic solvent. Okay, now that process is commercially operated, but it's tremendously sensitive to atmospheric conditions, and there have been numerous really serious fires and so on. So there are very significant safety concerns. And again, one of our projects over the last few years has been to develop alternative electrolytes for this aluminium process using less flammable sources of aluminium, even to the extent where we can build, this is a pilot scale unit that we built at a commercial electroplaters working with partners including Airbus. So this is an example where we've again sought to understand the chemistry of aluminium reduction in order to try to avoid using, in this case, these rather dangerous sources and solvents. And we often get money from government sources such as Innovate UK or funders in Europe to work in this way. All right, so I'm kind of moving on. And I did mention earlier that one of our key interests was in energy, because everything now, isn't it, is about energy. What do we use? How do we store it? How do we recover it? And at the moment, we're shifting. We're in a real transition as a society, moving towards what we think of as being more sustainable uses and sources of energy, and particularly batteries. So one of our focuses in this center within the school has been to ask questions about current battery chemistries. You know, how can we improve the efficiency? Can we use different materials which are cheaper, more sustainable, and less environmentally damaging? So that has taken, in a sense, two parts. We've looked at maybe new systems, and we've looked at ways of recovering and making older systems more efficient. So our new battery chemistries have focused on metals like aluminium and zinc. And again, we've sought funding from European agencies, and more recently from, Andy mentioned earlier, from the UK Faraday Institution, in order to develop these chemistries to understand the recycling processes and new battery chemistries. So one of these has been on aluminium. So we're now looking at ways of perhaps the next generation technology. Everything at the moment is about lithium. All the key technology, batteries, computers, phones, cars, it's all lithium at the moment. And you might think, well, okay, that's great. What's the problem? Well, there is an inherent problem, because much of the lithium that we use for these new batteries is in places which are often either difficult to get to or have some sort of geopolitical sensitivity. So a lot of the lithium we get, for example, is coming from China. So, you know, we have to think about our relationships with these supply companies. But wouldn't it be great if we could use a material that was just abundant everywhere? Okay, and aluminium is. The other thing about lithium is, and of course we think of batteries as a green technology. If you've got an electric car, it's great and it's clean where we're using it on the streets of Leicester. But what about where it's being made, and what about what happens to it afterwards? So these are things that we have to think about in our society now. It takes 2,000 tons of water to make a ton of lithium. Okay, so you need a huge amount of water, and much of the lithium that we find is in very dry and arid regions. Okay, so there are social implications about this, because water is sometimes redirected from poorer communities in order to feed the manufacturing processes for the richer nations. So all of these are really, really important. So lithium is great, but it would be nice if we had a more abundant alternative. And aluminium is almost as good in terms of its energetic properties and its lightweight as well. So this is what's motivating us at the moment to look at aluminium as an alternative to lithium batteries. And again, we have European funding for that, which is active now. So as I kind of approach the end of this, I'm going to throw a little bit more science at you now, because one of the things that we often have to do is use facilities that we don't have in our labs in Leicester. So we often apply for time and use the large-scale scientific facilities that are present throughout Europe, and also in the UK. This is a photograph I took of a team visit to one of the spectroscopic facilities at the Rutherford Appleton lab, which is in Oxford. And this is actually doing some neutron beam scattering studies on materials, on thin film materials. So really hardcore science funded by the large scale facilities, again underpinning some of these what you might think of as applied applications. All right then, well I'll come to the last thing on my list of activities, which I think really has been something which is relatively new, but I think we all see this now as being a really important strategic development, and that is on looking at recycling technologies. So taking again the lithium-ion battery as an example, we're producing more and more lithium-ion battery cars, and actually up until now, nobody's really been thinking about what do we do with these cars when the batteries run out or when the batteries cease to exist? What do we do with the materials? How do we recover them in order to be able to reuse them? And so a lot of the science that we're doing now has been focused on understanding the technologies that are currently limiting the lithium-ion batteries, understanding the materials that are present, the chemical and molecular interactions between these materials, so that we can design the next generation of lithium batteries in such a way as it makes them much, much easier to recover, to disassemble, and to reuse. So that is our motivation behind the recycling technologies. And we've been lucky enough actually to, as Andy said, to have been funded by the Faraday Institution with a group of others. And that quite recently resulted in a really nice paper that we managed to publish in Nature, talking about all these challenges of addressing energy needs and recycling technologies. Okay, well, that's kind of miraculously, I'm almost on time, which is very unusual for those of you who know me. And I'll finish my kind of formal presentation by just showing you this summary slide. So what I really wanted to kind of get over to you is that I've shown you a lot of examples of projects where we've worked with particular technologies and particular partners, but all of that has been underpinned by a fundamental knowledge of the chemistry and of the physical science. And that, of course, is what we do as researchers. That is what you would do as an undergraduate project researcher. And Andy mentioned publications. Just now, we're waiting for the final referee's comments of a paper that we've published with one of our final year MChem undergraduate students on aluminium batteries. So we're very keen to involve our undergraduates in the research process. Within the center, they will have access to, you will have access to our instrumentation and what's going on here. And so it's chemistry fundamental that's underpinning the science and developing these technologies. And I've kind of included here a list of what I've spoken about. So surface processing, manufacturing, that I mentioned, the plastic wood, energy, recycling, and forensics. And one of our key points here is that we not only do the fundamental science, but we work with the people who will want it, who will be able to use it, and ultimately to commercialize that. Okay, so I've spoken for long enough. I think I've used up my available time. I'm happy now to finish and to take any questions.
Thank you very much. That was very interesting and informative. Does anyone have any questions at all, or anything they might like to comment?
I have a little comment, Karl, that's really fascinating. Like so many different topics in your research groups. Also, I like how they interpenetrate each other. They have a common theme, and then they just explode in like so many different directions. It's brilliant. Regarding the lithium batteries, because I know that the big sell on lithium in general was, oh, it's the lightest element, so it kind of makes sense to pack as much as possible in a battery because we can put a lot of it. So I'm a group 2 chemist, and I know there's a lot of stigma behind beryllium because it's very, very toxic. But ultimately, beryllium has very, very similar properties to lithium. It's light, it's abundant, it's more abundant than lithium, actually. But ultimately, a battery is like a very well-defined entity, very confined. We're not really worried about releasing the environment of a battery, do we? Like, if anything, we want to get it back to try and recycle it, as you're saying. So would there be any problems developing batteries with beryllium, you think?
So okay, so there's a couple of things there. I think beryllium would be a hard sell in the current environment because of environmental concerns, toxicity concerns. And you rightly say that, you know, we use batteries most of the time, and we don't have any interaction with what's inside them. But every now and then you'll open up a torch or or something which it's been in the cupboard for a while, and you'll see that it's leaked out the acid or the zinc salts or whatever it is that powers that cell. So there are, one has to plan for release of the contents into the environment, just as you might if it was damaged in a collision, for example, in a car. So I think beryllium would be a hard sell, but there's also a technological and a scientific issue. So lithium, of course, is only one positive charge. It's also very light. So if we know what the energy is associated with that charge, or recycling it from the metal to lithium plus, and we divide by the mass, then that gives us what's known as the energy density. And what we're looking for is something that has high as possible energy density. Even a lithium-ion battery, by the way, is about 1/10 of the energy density of fossil fuel. So so beryllium would be quite good in that respect, but also there are other metals, magnesium and particularly aluminium. Now aluminium is about 4 times heavier than lithium, but it has 3 electrons. It has a 3+ charge. So the 3+ divided by the 4 times weight means that it's almost as good in energy density terms as lithium. But the problem, the difficult chemistry, comes from the way that those 2+ and 3+ ions interact with the materials that hold them. And this is really hardcore materials chemistry, structural chemistry. The most elegant and wonderful thing about lithium batteries is that the lithium ions pop in and out of the materials which store them. So graphite in the anode, and often a metal oxide like cobalt or nickel or manganese in the cathode. And these materials, they store the lithium ions, and they just come in and out and reversibly. Now, when you replace those lithium ions with something like aluminium, or in this case, your question was beryllium, the 2+ metal ion goes into these materials, but because they're a similar size and they have more charge, they like it more, so they stick. Okay, and so the beryllium, the aluminium, magnesium ions, they don't work in the same way as lithium, because the materials that we use to store the metal ions don't let them go again, because they're much more strongly bound. And that's really one of the challenges for the chemistry of magnesium and aluminium batteries in particular. Does that answer your question?
Yeah, thanks. So, I'm aware that obviously that any material needs to live a full life cycle. It's eventually someone, even like, let's say in 1,000 years, we need to think about, I don't know, maybe someone will find a storage of all the batteries that we decided not to use, and then
sure,
we need to deal with that as well. So, thank you.
Does anyone else have any other questions at all?
I have a question, if that's okay.
Yeah.
You've answered my first 20 questions already, Karl, so thank you for that. I guess I was thinking about it from people who do research and people who work on batteries from an industry perspective. So could you just give us a sense of those people that are still working on lithium-ion batteries in order to improve them, and then those that are looking at alternatives like yourself in terms of aluminium batteries, and whether you think that will be a direct replacement to lithium batteries, or where you think it will just be an alternative that we will be able to purchase as a consumer, because the lithium-ion battery technology will improve as a result of this new battery coming onto the market that could be considered quite disruptive.
Okay, so the vast majority of activity at the moment is focused on improving lithium ion and developing more recyclable and more sustainable process. So remember, the battery is a combination of essentially 3 things: the anode, the cathode, and the electrolyte in between. And all of those components have a really important role to play. So there's a huge amount of activity in developing new cathode materials, things like sulfur. You might have heard of lithium sulfur batteries. And relatively little in terms of what comes next. I mean, it's happening amongst the academic community, and certainly companies are working on those things. But at the moment, it's really all about how can we make more lithium batteries more effective, more efficient, longer living, higher power. And then the community over the last 5 years or so has just really started to think about, hang on, what do we do with all that sort of stuff that's left? So that's what's happening at the moment, really. The new alternatives, the next generations are some way away.
Okay, thank you for that, Karl.